our planet Earth, a sphere of life, a cosmic oasis. But what lies beneath its surface? What mysteries are hidden within its depths? Join me on a journey to the center of the Earth. We will travel through layers of rock, metal, and intense heat. Our destination, the heart of our planet. This is not a journey for the faint of heart, it is a journey for the curious, for those who yearn to understand the world around them. We will encounter extreme conditions, forces that shape continents and power volcanoes, but the rewards will be great. This journey will take us back in time to the formation of our planet. We will witness the forces that have shaped Earth over billions of years. We will gain a new appreciation for the delicate balance that makes life possible. So, prepare yourself for an adventure unlike any other. We are about to embark on a journey to the center of the Earth. Fasten your seatbelts and let the exploration begin. Imagine Earth as a giant onion with layers stacked upon layers. Each layer has its own unique properties, composition, and story to tell. Our journey will take us through each of these layers, starting with the outermost layer, the crust. Beneath the crust lies the mantle, a thick layer of hot, dense rock. It is a place of constant motion, where heat from the Earth's core drives the movement of tectonic plates. This movement is responsible for earthquakes, volcanoes, and the formation of mountains. Deeper still, we encounter the outer core, a layer of liquid iron and nickel. This swirling mass of molten metal generates Earth's magnetic field, a protective shield that deflects harmful radiation from the sun. Finally, we reach the inner core, a solid sphere of iron and nickel at the very center of our planet. It is a place of immense pressure and heat, hotter than the surface of the sun. Our journey is not just one of imagination. It is a journey guided by science, by the tireless work of geologists, geophysicists, and other scientists. Through their research, we have been able to piece together the story of Earth's interior, even though we cannot directly observe it. Seismology, the study of earthquakes, has been instrumental in mapping Earth's interior. By analyzing the way seismic waves travel through the Earth, scientists can determine the density and composition of different layers. Laboratory experiments simulating the extreme conditions found deep within Earth have also provided valuable insights. By subjecting minerals to high pressures and temperatures, scientists can study their behavior and understand how they form. Our understanding of Earth's interior is constantly evolving as new discoveries are made. This journey is a testament to the power of human curiosity and our relentless pursuit of knowledge. As we embark on this journey, prepare to be amazed. We will encounter wonders beyond our wildest imagination. We will witness the raw power of nature and the intricate processes that have shaped our planet. We will learn about the formation of diamonds, created under unimaginable pressure deep within the Earth. We will discover strange and wonderful creatures that thrive in the depths of the ocean, far from the reach of sunlight. But most importantly, we will gain a deeper appreciation for the planet we call home. We will understand how Earth's interior is interconnected with its surface, influencing everything from the air we breathe to the continents we live on. So, let us begin our descent, our journey to the center of the Earth, a journey of discovery, wonder, and a profound understanding of the world beneath our feet. Our journey begins with the Earth's crust, the outermost solid layer of our planet. Imagine it as the skin of an apple, a thin and fragile layer compared to the vastness within. Despite its relative thinness, the crust is incredibly dynamic, constantly changing and reshaping itself over millions of years. The crust varies in thickness, ranging from a mere 3 miles beneath the oceans to an average of 25 miles beneath the continents. This difference in thickness is due to the different types of crust: oceanic crust, which is denser, and continental crust, which is lighter. This variation in thickness plays a crucial role in the movement of tectonic plates, which we will explore later. The crust is not a uniform layer, but is broken into several large pieces called tectonic plates. These plates float on the semi-fluid layer of the mantle beneath them, constantly moving and interacting with each other. This movement is responsible for earthquakes, volcanoes, and the formation of mountain ranges. As we delve deeper into the Earth, we will leave behind the familiar landscapes of mountains, valleys, and oceans. The crust, with all its beauty and complexity, will fade above us as we venture into the hidden depths of our planet. The Earth's crust is a mosaic of different rock types, each with its own unique story to tell about our planet's history. The most common elements in the crust are oxygen and silicon, which combine to form various silicate minerals. These minerals, along with others, make up the rocks that form the continents and ocean floors. Igneous rocks formed from the cooling and solidification of magma or lava dominate the Earth's crust. Granite, a common igneous rock found on continents, is known for its durability and beauty. Basalt, another igneous rock, forms the ocean floors and is characterized by its dark color and fine-grained texture. Sedimentary rocks, formed from the accumulation and cementation of sediments, tell the story of Earth's past environments. Sandstone, formed from ancient beaches and deserts, and limestone, formed from the remains of marine organisms, provide clues about Earth's climate and life forms millions of years ago. Metamorphic rocks, formed when existing rocks are subjected to intense heat and pressure, reveal the powerful forces at work within the Earth. Marble, a metamorphic rock formed from limestone, is prized for its beauty and is often used in sculptures and buildings. The crust is a treasure trove of minerals, from the common quartz and feldspar to the rare and valuable diamonds and rubies. These minerals not only provide us with resources but also offer insights into the geological processes that have shaped our planet. The Earth's crust is the stage upon which all of life unfolds. It provides the solid foundation for our cities, the fertile soil for our crops, and the breathtaking landscapes that inspire us. The crust is not merely a platform for life, it is intertwined with the very existence of living organisms. The weathering and erosion of rocks provide essential nutrients to the soil, supporting the growth of plants. These plants, in turn, form the basis of the food chain, providing sustenance for animals and humans alike. The oceans, vast bodies of water that cover most of the Earth's surface, are in constant interaction with the crust. The chemical exchange between seawater and the ocean floor influences the composition of both, playing a crucial role in regulating Earth's climate. Humans have long relied on the Earth's crust for resources. We extract minerals from the ground to build our homes, manufacture our tools, and power our technologies. The crust provides us with fossil fuels such as coal, oil, and natural gas, which we use for energy. However, our exploitation of the Earth's crust has also had significant consequences. Mining activities can scar landscapes and pollute water sources. The burning of fossil fuels releases greenhouse gases into the atmosphere, contributing to climate change. The Earth's crust is not a static shell, but a dynamic system constantly in motion. This movement is driven by the heat deep within the Earth's interior, creating convection currents in the mantle. These currents cause the tectonic plates, which make up the crust, to slowly drift and interact with each other. This process is known as plate tectonics. The interactions between tectonic plates are responsible for some of the most dramatic events on Earth. When two plates collide, they can buckle and fold, creating towering mountain ranges like the Himalayas. The collision of the Indian and Eurasian plates, for example, continues to push up the Himalayas at a rate of about 5 millimeters per year. When plates move apart, magma from the mantle rises to fill the gap, creating new crust. This process, known as seafloor spreading, is responsible for the formation of mid-ocean ridges, vast underwater mountain ranges that encircle the globe. The Mid-Atlantic Ridge, for example, is a testament to the ongoing process of seafloor spreading, where the North American and Eurasian plates are pulling apart. The movement of tectonic plates can also cause earthquakes, some of the most destructive natural disasters on Earth. When plates grind past each other, stress builds up along their boundaries. This stress is eventually released in the form of seismic waves, causing the ground to shake violently. The Earth's crust is a treasure trove of resources and natural wonders. From minerals to energy sources, the crust provides materials for survival and progress. It also houses awe-inspiring natural wonders. Deep within, diamonds form under intense heat and pressure. These gems, prized for their beauty, showcase Earth's power. Caves reveal hidden worlds beneath our feet. Adorned with stalactites, they host unique ecosystems. Volcanoes, both destructive and beautiful, create new land. They release valuable minerals into the environment. The Hawaiian Islands are volcanic formations. The Earth's crust is dynamic and essential. It is our home and a source of wonder. As we journey to the Earth's center, we appreciate its complexity and beauty. Our journey now takes us past the Earth's crust, leaving behind the familiar landscapes of mountains, valleys, and oceans. We are entering the Mantle, a vast and mysterious realm that makes up the majority of our planet's volume. If the Earth were an apple, the mantle would be the thick, fleshy part between the thin skin and the core. The mantle begins just a few miles beneath the ocean floor and extends downwards for approximately 1,800 miles. This immense thickness means that the mantle experiences a wide range of pressures and temperatures, increasing dramatically as we descend deeper. The pressure at the bottom of the mantle is over 2 million times greater than the pressure at sea level, enough to crush even the strongest materials. Despite the intense conditions, the mantle is not a molten sea of magma as one might imagine. Instead, it is composed mostly of solid rock, albeit rock that behaves in very unusual ways due to the extreme heat and pressure. The mantle's composition, primarily silicate minerals like olivine and pyroxene, holds clues to the early formation of our planet and the processes that continue to shape it. As we venture deeper into the mantle, the darkness will be absolute, the silence broken only by the faint rumblings of a planet in constant motion. We are entering a realm where the very rocks flow like a viscous fluid over geological timescales, a place of unimaginable power that drives the movements of continents and the creation of volcanoes. Our journey now takes us past the Earth's crust, leaving behind the familiar landscapes of mountains, valleys, and oceans. We are entering the Mantle, a vast and mysterious realm that makes up most of our planet's volume. If the Earth were an apple, the mantle would be the thick, fleshy part between the thin skin and the core. The mantle begins just a few miles beneath the ocean floor and extends downwards for approximately 1,800 miles. This immense thickness means that the mantle experiences a wide range of pressures and temperatures, increasing dramatically as we descend deeper. The pressure at the bottom of the mantle is over 2 million times greater than the pressure at sea level, enough to crush even the strongest materials. Despite the intense conditions, the mantle is not a molten sea of magma, as one might imagine. Instead, it is composed mostly of solid rock, albeit rock that behaves in very unusual ways due to the extreme heat and pressure. The mantle's composition, primarily silicate minerals like olivine and pyroxene, holds clues to the early formation of our planet and the processes that continue to shape it. As we venture deeper into the mantle, the darkness will be absolute, the silence broken only by the faint rumblings of a planet in constant motion. We are entering a realm where the very rocks flow like a viscous fluid over geological timescales, a place of unimaginable power that drives the movements of continents and the creation of volcanoes. Section 2, a mantle of rock composition and properties. The mantle, though primarily solid, behaves very differently from the rocks we are familiar with on the Earth's surface. The intense heat, thousands of degrees Fahrenheit, weakens the bonds between atoms within the mantle rocks, allowing them to deform and flow very slowly over millions of years. This ability to flow, known as plasticity, is what allows the mantle to drive the movement of tectonic plates. The composition of the mantle is not uniform throughout. The upper mantle, closer to the crust, is composed mostly of peridotite, a dense, dark-colored rock rich in olivine and pyroxene. As we descend deeper into the lower mantle, the pressure increases, causing the minerals to rearrange themselves into denser forms. This region is thought to be dominated by minerals like bridgmanite and periclase, which are stable under such extreme conditions. The mantle's composition has been pieced together through a combination of studying volcanic rocks, which offer glimpses into the mantle through their chemistry, and analyzing seismic waves from earthquakes. These waves travel at different speeds through materials of different densities, allowing scientists to create a sort of ultrasound image of the Earth's interior. Understanding the composition and properties of the mantle is crucial for understanding how our planet functions. The mantle's slow churn drives plate tectonics, generates Earth's magnetic field, and influences volcanic activity, all processes that have profound impacts on life on the surface. Section 3. Convection currents. The mantle's slow churn. The mantle is in constant motion, driven by heat from the Earth's core and the decay of radioactive elements within the mantle itself. This heat creates convection currents similar to the currents in a pot of boiling water, but on a much grander scale and at a much slower pace. Imagine the mantle as a giant lava lamp, with hot, less dense material rising from the core mantle boundary towards the Earth's surface. As this material rises, it cools and becomes denser, eventually sinking back down towards the core where the cycle begins again. These convection currents are incredibly slow, moving at a rate of just a few centimeters per year, about the same rate that your fingernails grow. These slow-moving currents may seem insignificant, but they are the driving force behind plate tectonics. The rising limbs of these currents push on the underside of tectonic plates, causing them to move apart, while the sinking limbs drag plates back down into the mantle. This constant tug-of-war between convection currents shapes the Earth's surface, creating mountains, oceans, and continents over millions of years. The mantle's convection currents are also responsible for transferring heat from the Earth's hot interior to its surface, playing a crucial role in regulating our planet's temperature. Without this heat transfer, the Earth's surface would be a much colder and less hospitable place. Section 4. Tectonic dance. The mantle's role in shaping Earth. The mantle's convection currents choreograph the movements of Earth's tectonic plates, creating mountain ranges, ocean trenches, and causing earthquakes. Section 5. Volcanic fury. The mantle's fiery breath. Volcanoes form when magma from the mantle erupts, creating new landforms and influencing Earth's climate. Volcanic eruptions, while destructive, contribute to fertile soils and are essential for Earth's natural cycles. Section 1. The liquid heart entering the outer core. We now enter the outer core, a churning ocean of molten iron and nickel, hotter than the sun's surface. This liquid metal layer drives Earth's magnetic field, a protective shield essential for life. The outer core's extreme environment challenges our understanding of matter. Section 2. A sea of iron composition and properties. The outer core, primarily composed of iron and nickel, churns due to heat from the inner core and Earth's rotation. This fluidity is crucial for generating Earth's magnetic field. The outer core's motion powers Earth's magnetic field, shielding us from harmful solar radiation. This magnetic field is generated by the dynamo effect, where the movement of liquid iron creates electric currents. Earth's magnetic field extends into space, forming the Magnetosphere, which deflects harmful solar particles. This dynamic shield protects our atmosphere and allows life to thrive. During strong solar winds, the magnetosphere creates stunning auroras near the poles. Earth's magnetic field is a navigational tool for humans and animals. Compasses align with magnetic field lines, aiding navigation. Many animals, like migratory birds and sea turtles, use the magnetic field for orientation and migration. Our journey now takes us to the inner core, a solid sphere of iron and nickel. The pressure here is immense, over 3.5 million times sea level pressure. The inner core's extreme conditions hold clues to Earth's formation and processes. The inner core, despite its extreme temperature, remains solid due to immense pressure. It is primarily composed of iron, with a crystalline structure. This solid state influences Earth's magnetic field and overall stability. The inner core's temperature reaches around 9,800 degrees Fahrenheit. The pressure is over 3.5 million times sea level pressure, keeping the iron solid. Studying these extreme conditions helps us understand planetary formation and magnetic fields. The inner core, hidden deep within our planet, plays a crucial role in generating Earth's magnetic field, a protective shield that makes life possible. While the liquid outer core is the engine of the geodynamo, the inner core is vital in this system. Imagine the inner core as a giant, spinning, solid iron ball within the swirling liquid outer core. The inner core spins slightly faster than the mantle, stirring the liquid iron in the outer core. This motion, coupled with convection currents, generates electric currents in the outer core. These currents create a magnetic field extending into space, forming the magnetosphere. This field deflects charged particles from the solar wind, protecting life on Earth. Our journey to the center of the Earth has taken us to the very heart of our planet, a place of unimaginable extremes and profound mystery. While we have learned much about the inner core, many questions remain unanswered, beckoning future generations to unravel the secrets hidden deep within our planet. We still do not fully understand the exact composition of the inner core beyond the predominant iron and nickel. What other elements are present, and in what quantities? Future exploration will require innovative approaches and technologies. The journey to the center of the Earth is a quest to understand the very heart of our planet. It is driven by human curiosity, a desire to push the boundaries of knowledge and explore the hidden wonders of our world. From the vantage point of space, Earth appears as a serene blue sphere, a tranquil oasis in the vast cosmic desert. Yet beneath this serene facade lies a heart of molten iron, a churning dynamo that silently orchestrates a symphony of forces essential for life's existence. The Earth's core, often overlooked in our daily lives, is the silent conductor of a planetary orchestra that sustains us all. The most profound influence of the core is its role in generating Earth's magnetic field, a protective bubble that shields us from the relentless barrage of charged particles streaming from the sun. This magnetic field, a product of the core's churning dance of liquid iron, acts as a planetary shield, deflecting most of these harmful particles, preventing them from stripping away our atmosphere and bombarding the surface with deadly radiation. Without this invisible shield, life as we know it would cease to exist. The sun, our source of life-giving light and warmth, would also be our undoing. Its intense radiation sterilizing the surface, turning our oceans into boiling cauldrons, and stripping away our atmosphere, leaving behind a barren, lifeless rock. The Earth's core, in its silent, unseen fury, provides the essential ingredient for life to flourish, a stable, hospitable environment. It is a reminder that the forces that shape our planet are not always visible, but their influence is woven into the very fabric of our existence. Section 2. A magnetic guardian shielding life from cosmic fury. The vastness of space, while awe-inspiring in its beauty, is also a realm of constant bombardment from high-energy particles, a cosmic rain of radiation that would be deadly to life on Earth. This is where the Earth's magnetic field, generated by the core's dynamo, steps in as a silent guardian, deflecting this cosmic onslaught and protecting the delicate balance of life on our planet. Imagine the Earth's magnetic field as a giant invisible umbrella shielding us from a downpour of harmful radiation. This shield, known as the Magnetosphere, extends far out into space, deflecting most of the charged particles carried by the solar wind, a stream of high-energy particles constantly flowing from the Sun. Without the Magnetosphere, the solar wind would strip away our atmosphere, exposing us to the full brunt of the Sun's ultraviolet radiation. This radiation would break down water molecules in the atmosphere, leading to the loss of our oceans over time. The surface would be bombarded by harmful radiation, making it impossible for life to survive. The magnetosphere is not a static barrier, but a dynamic shield, constantly buffeted by the solar wind. During intense solar storms, when the Sun releases massive bursts of energy and charged particles, the magnetosphere can be compressed, allowing some particles to penetrate the atmosphere near the poles. These particles interact with the atmosphere, creating stunning auroras, the northern and southern lights, a visible reminder of the invisible shield protecting us. Section 3. Orienting in a magnetic sea, navigational aids from the deep. The Earth's magnetic field, a product of the core's churning dynamo, provides a subtle navigational grid, guiding both human explorers and migrating animals. This invisible grid has been a silent guide for millennia. For centuries, humans have relied on the compass, harnessing the Earth's magnetic field for navigation. The compass needle aligns with the Earth's magnetic field lines, pointing towards the magnetic poles. This principle has allowed sailors to cross oceans and explorers to chart new lands. Many animals also use Earth's magnetic field for navigation. Migrating animals possess an innate ability to sense the Earth's magnetic field. Birds, sea turtles, and insects have evolved biological magnetoreceptors to detect magnetic variations. These animals use this sense to orient themselves and find their way back to specific grounds. The Earth's magnetic field provides a reliable guide for these remarkable feats of navigation. Section 4. A delicate balance, disruptions and the future of life on Earth. The Earth's core, a churning dynamo deep within our planet, is a powerful reminder of the interconnectedness of Earth's systems and the delicate balance that sustains life. While the core has provided a stable environment for billions of years, its activity is not static, and disruptions, though rare, can have profound consequences for life on the surface. Variations in the Earth's magnetic field strength and orientation, linked to processes within the core, can impact our technological infrastructure. Solar storms, capable of disrupting satellites, communication systems, and power grids, highlight our vulnerability to the core's influence. Understanding these variations and developing mitigation strategies are crucial for a technologically dependent society. The Earth's magnetic field is not a constant shield. Geologic records indicate that the magnetic field has flipped numerous times in Earth's history, with the magnetic north and south poles reversing positions. These flips, though not fully understood, are thought to be related to changes in the flow of liquid iron in the outer core. While these flips occur over thousands of years, the period of transition, when the magnetic field weakens and becomes more complex, could pose challenges for life on Earth. Increased exposure to cosmic radiation during these periods could have detrimental effects on organisms, potentially leading to mutations, extinctions, and disruptions to ecosystems. Section 1. Reflections from the Center. A journey's end, a deeper understanding. Our journey to the center of the Earth has come to an end, but the insights gained will resonate long after we've returned to the familiar surface. We ventured into the heart of our planet, not with pickaxes and dynamite, as in Jules Verne's fantastical tale, but with the tools of scientific inquiry, seismology, physics, and an insatiable curiosity to comprehend the world beneath our feet. We've traversed layers of rock, each telling a story of immense pressure and heat, of formation and deformation over eons. We've witnessed the Earth's mantle, not as static layers in a textbook diagram, but as a slow, churning engine, driving the very continents we inhabit. Deep still, we encountered a realm of liquid metal, the Earth's outer core, a churning dynamo generating the magnetic field that is our shield against the cosmos's fury. And finally, at the very heart of it all, the inner core, a sphere of solid iron, a testament to the unimaginable pressure found at the planet's center. But more than just a collection of facts and figures, our journey has instilled a profound appreciation for the interconnectedness of it all. The Earth's core is not some remote entity detached from our surface world. It is the very heartbeat of our planet, driving the processes that shape our landscapes, influence our atmosphere, and ultimately make life possible. Section 2, Earth's Hidden Heart, a legacy of discovery, a future of exploration. As we return to the surface, bathed in the warmth of the sun, we carry with us a profound sense of gratitude for the Earth's core, a hidden heart that sustains us all. The journey, however, does not end here. It continues in the relentless pursuit of knowledge, in the scientific endeavors that seek to further unravel the mysteries of our planet's depths. Imagine the advancements yet to come. Sophisticated sensors that listen to the Earth's rumblings with even greater clarity, powerful computer models that simulate the complex interactions within the core, and perhaps one day, the ability to directly sample the materials of this extreme environment, holding in our hands pieces of the Earth's heart. Each discovery will add to the legacy of those who came before. From the early pioneers who first dared to imagine a world beneath the surface to the modern scientists who continue to push the boundaries of our understanding. And as we learn more about our own planet, we inevitably gain insights into the workings of other worlds, enriching our comprehension of the vast and awe-inspiring universe we inhabit. The journey to the center of the Earth may remain a physical impossibility for now, but the journey of discovery, the quest to comprehend the hidden workings of our planet, that is a journey without end, a testament to the boundless curiosity of the human spirit.